Okay, so something we discussed in lecture on Friday the 19th of January was solving for isotope problems where they ask you to find the percent abundances rather than an additional mass or the identity of an unknown element. Now, when we're solving for percent abundance problems, we're usually given a table, okay, and in that table we are given the element, okay, we know what the element is, and then we're given its two isotopes, and then it's that specific isotope's mass, and then it asks us to solve for the percent abundances of each. Now this poses a problem because that becomes a two-variable problem where we have two variables that are unknown and three variables that are known, and we can't solve them that way, so we have to solve by substitution. So we can use what we know about isotopes and their natural abundances to help us with that substitution. So we know that our average mass, A, is going to be equal to the mass of the first isotope times its percentage, and then we're going to add on the mass of our second isotope and its percentage, and so on and so on. Now the problem we're going to look at today, or the derivation that we're going to look at, we're just going to look at two isotopes. Okay, so our problem has two isotopes. If you were to have more, then you would have additional terms at the end of this equation. So in this problem, we would know A, we would know M, and we would know M. Okay, that would be given to us by the table and the periodic table. We just don't know P1 and P2. But what we do know is that P1 plus P2 is equal to 100%. Now, when we're doing isotope problems, we want to take things out of the percentage when we're doing the problem itself. Okay, we can always convert it back to a percentage, but when we're solving these problems, we cannot have things in percentage form. So I'm going to rewrite this as P1 plus P2 is actually equal to 1. So what we can do is we can pick a variable to solve for and then plug that in for the other variable in the equation. So in class, I solved for P1, and I said that P1 was equal to 1 minus P2. So we solved that in class. Those notes are posted on e-learning for you to review. But what I want to do today is actually solve for P2. So P2 is going to be equal to 1 minus P1. Now, it seems very similar in what we're solving for, but I promise the negatives work out a lot easier here when you solve for P2. So I'm sorry that I solved for P1 and made it that much more difficult in class. I should have solved for P2, so we're going to solve for P2 and plug that in this derivation here. But you can do it either way. Both ways will come out with the same exact answer, okay? So whatever way you're most comfortable, whatever equation that we end up with from this or from class, whichever one you want to use, go for it. It's all the same information, just solved algebraically differently to get the same value, okay? So either way that you do this is fine. So I'm going to use this equation, and I'm going to plug in P2 is equal to 1 minus P1. So we are going to get that the average mass is equal to M1 times P1 plus M2 times 1 minus P1. Okay, so we're going to distribute our M2s in to here. A is equal to M1 P1 plus M2 minus M2 times P1. I have two terms that both have a value of P1, which we're going to see as like an X value, an unknown value. So we're going to factor out that P1. Okay, so that's going to give me A is equal to P1 times M1 minus M2 plus M2. Okay, so I have this and this that I combined together, so I made sure to keep my negative sign in there. Okay, and then my plus M2 is there on the end. Okay, so I just factored out that P1 since they both had a common variable in them. Now I can then subtract both sides, subtract M2 from both sides, so I get A minus M2 is equal to P1 times M1 minus M2. I would now want to solve for P1. I want to isolate it on one side of my equal sign. So I'm going to divide both sides by M1 minus M2. And we get that A minus M2 divided by M1 minus M2 is equal to P1. Okay, so here is that final equation, which if you compare it to your notes in class, looks very similar to what we solved for when we solved for P2. So now once we have P1, so if P1 is given a value, we can solve for P2 because we know that P2 is equal to 1 minus P1. Okay, and that will give us P2. And then we just have to remember to convert back to percentages for our final answer. Okay, so let's run through this again. So we know that the average mass is going to be equal to the mass of each isotope multiplied by its percent abundance. The problem that we're looking at here, we don't know the percent abundances. But what we do know is that the sum of those percent abundances has to equal 100% or 1. So we're going to have to do some substitution into our equation. So we said that P2 is equal to 1 minus P1 and plugged that in for P2 into our equation. Meaning that now we have an equation that is only dependent on one unknown variable, P1. Okay. So we plug that in and we distribute our M2 into our parentheses, and then we isolate our variables that are dependent on P1. So that's how we get P1 times M1 minus M2, and then R plus M2 that comes out. Now we just have to algebraically solve. So we subtracted both sides by M2, then divided both sides by M1 minus M2 in order to isolate P1, and that's how we get our final answer of P1 is equal to the average mass minus the mass of the second isotope divided by the mass of the first isotope minus the mass of the second isotope. Okay, and remember, this average mass comes from the periodic table. Okay, so once you solve for P1, you're going to get some value for it, some number. You're then going to plug that number back into our original substitution equation in order to solve for P2. And then once you have those two values, you'll convert it back to the percentage, which you can then input for your answer in your ALEKS homework.